many fields of modern industry, electric arc welding is accomplishing miracles of production. Powerful diesel-electric locomotives are being made lighter and stronger by using arc welds in place of bolts, rivets, and castings. These penstock tubes at Shasta Dam were arc welded to eliminate all joints which might otherwise leak or corrode. New methods of ship construction have resulted from the use of arc welding, which speeds up production and produces a lighter, more rigid ship. In the manufacture of aircraft, arc welding on engine mounts, fuselages, and landing gear ensures maximum strength with a minimum of weight. But the successful application of arc welding depends on the use of proper welding methods. Here's what happens when improper welding methods have been used. Distortion has caused this job to warp out of shape. The same thing has occurred to this metal tray. The purpose of this film is to show how all distortion can be controlled and prevented. But first of all, we must understand what causes distortion. Let's start with this ordinary steel bar. If the bar is heated thoroughly and uniformly throughout its entire volume, considerable expansion in all directions will take place. Now, if the bar is allowed to cool evenly, without restraint of any kind, we know that it will contract to its original shape and size without distortion. However, if we place the two ends of the bar in a vise and then heat the bar uniformly, expansion in these directions will be prevented by the vise, and expansion can only occur in these other directions. As the bar cools, it contracts evenly in all directions. The result is a shorter bar with a greater thickness. Now let's go back to our original bar and see what happens when we heat only one side. Getting up close, we see that expansion in this case is localized and uneven. The surrounding cool metal acts similar to the vise and restrains expansion in these directions. But there is no resistance to expansion in this direction. It is obvious that this uneven expansion causes an unnatural displacement of metal. When this area starts to cool and contract, a small amount of that displacement becomes permanent. In other words, there was no control, and the final result is distortion. Now, several steel bars, side by side, is much the same as a steel plate, showing that uncontrolled contraction always causes distortion. Let's see what actually happens when we make this butt weld. Now, keep the picture of that steel bar in mind, because the bar's behavior when heated is very similar to the weld bead will form to join these two plates. As the weld progresses, we can see that the molten weld metal begins to cool and contract immediately, while at the same time, the heat of the arc itself is causing considerable expansion ahead of the contraction. Looking at the end view, we can see that the intense heat of this molten weld metal, plus the heat of the arc itself, is being transmitted to the surrounding areas. It is important to understand that while the weld metal is cooling, and therefore contracting, the temperature of the surrounding plates is rising, and therefore causing considerable uneven expansion. As these plates cool, they will also contract. When we allow expansion and contraction to occur without any control, the result is bound to be distortion, caused by this tough-looking villain, Mr. Shrink himself. He thinks he's pretty powerful, but we can show that Shrink is all brawn and no brain. We know that on any welding operation, Shrink is always right on the job. Look at him pull, and look at the distortion. Now that the damage has been done, let's slice off a piece of the plate and examine a typical cross-section of the weld. The overwelding here is a waste of time and money, adds nothing to the strength and performance of the joint, and in this case, caused abnormal distortion. Let's find a rule we can apply in a situation of this kind. Rule number 1. To prevent distortion, reduce the effective shrinkage force. In other words, always use as little weld metal as possible and make better use of the weld metal you need. We can also reduce the effective shrinkage force through proper edge preparation. This amount of bevel would require more weld metal than necessary. To obtain proper fusion at the root of the weld, with a minimum of weld metal, the bevel should be 30 degrees. But proper fit-up is also important. So, space the plates 1/32 to 1/16 of an inch apart. You will then need only a minimum amount of weld metal to produce a strong joint. Using fewer passes is another way of controlling distortion. For example, on plates that are free to move, distortion in this direction is always a problem. In this case, if we use 1 or 2 passes with large electrodes, we will greatly reduce distortion. In welding any structure, it is always important to consider the neutral axis. With a conventional fillet, the weld is so far off the neutral axis that shrink has plenty of leverage to pull the plates out of alignment. But use of the fleet fillet method places the weld close to the neutral axis, greatly reducing the leverage so that shrink cannot pull the plates out of line. Your own experience and ingenuity will uncover other methods. For example, intermittent welds frequently give all the strength required. In this way, you can use 2/3 less weld metal and reduce the effective shrinkage force by that much. On this bulkhead, good engineering design permitted the use of intermittent welds, which meet all strength requirements and at the same time minimize distortion. When a continuous weld is required, we can control distortion if we first understand how expansion affects the plates. Notice how expansion from the heat of the weld along the edges causes the plates to spread, as shown in the magnified circle. As the weld progresses, the spreading continues, and the plates become locked in this position by the cooling and contraction of the weld metal. Welding speed will determine the amount of this spreading action, but we can control this action and prevent distortion by the use of backstepping, whereby each successive bead is laid from right to left, but the direction of your welding progresses from left to right. To illustrate this method, very short welds are used here, but in actual practice, each bead is laid with 1 stick of electrode to allow time for the heat from each weld to distribute evenly throughout the plates before beginning the next bead. When we use backstepping, notice how heat from the first weld causes expansion which temporarily spreads the plates. But as the heat moves out across the plates, the expansion in these outer areas, acting against the bead which is cooled, forces the plates together. Each weld becomes a rigid section by the time the next weld is started, so that the spreading action becomes less and less with each succeeding bead, until the weld job is completed without further spreading or distortion. Rule number 2 gives us a little different slant on this fellow shrink. To prevent distortion, make shrinkage work for us. This is simply another way of saying that shrink is plain dumb and is just as willing to work for us as against us, providing we're smart enough to use him to our advantage. On a T-weld like this, we can anticipate Mr. Shrink's tendencies and tip the perpendicular plate slightly away from the weld side. Now, see how quickly Shrink goes to work for us and straightens this part up to its true position. Another adaptation of rule number 2 is the spacing of parts before welding. In welding these searchlight trunnion arms, which must be very accurately spaced when the welding is completed, allowance is made for the amount of shrinkage which will occur. Before welding, the parts are spaced like this. Then, when the welding is completed, watch how controlled shrinkage brings the two arms into correct position and perfect alignment. We can also make shrinkage work for us by pre-bending or springing the parts involved. For example, when these two plates are sprung away from the weld side, the counter force exerted by these clamps, holding the plates firmly, overcomes the shrinkage tendency of the weld metal, causing it to yield. But we can still use Mr. Shrink after the clamps are removed. Now all he needs to do is give the plates a slight pull to remove any signs of distortion. Pre-bending may be applied to any number of welding operations. Here, it is being employed on these steam shovel dipper sticks to make sure that the parts will be straight after welding. So far, we have illustrated several methods by which we can control and prevent distortion. First, by reducing the effective shrinkage force. And second, by making shrinkage work for us. But on certain types of weld jobs, we may still find that we have a distortion problem. Then, we must use other methods. We'll call this rule number 3. To prevent distortion, balance shrinkage forces with other forces. This rule applies automatically in welding this machine base, where its own structural nature provides rigid balancing forces. But when these natural balancing forces are not present, we can place Shrink in the position of using his own powerful force to balance itself. Here's how. Use proper welding sequence. By welding alternately on both sides of the neutral axis of these two plates, watch what happens to Shrink. First, he has to pull on this side, then rush around to pull on the other side, then back again, and over again. It's a much harder pull each time, until finally we have Shrink tired out completely. The result? No distortion. Here's another application of the same principle. Staggered intermittent welds, applied in this sequence. 1, 2, 3, 4. Proper welding sequence permitted the construction of this crane boom to proceed without delay and without distortion. The operation was thoroughly planned beforehand, so that each crossarm was tack welded to the main members to first make the entire crane a rigid structure. Following this, one set of crossarms was welded on one side. Then, one set on each opposite side, always balancing one shrinkage force with another. Step by step, right on up to the end, so that the final result was a perfectly straight crane boom. The use of peening is the application of a balancing force to prevent distortion in a different sense of the word. By peening the bead, we actually stretch the weld metal, counteracting its tendency to shrink as it cools.
When we use peening, Shrink really takes a beating. Look at him. He's groggy already. Peening takes the fight right out of him.
But don't overdo it. Too much peening may damage the weld metal. The most important method of overcoming distortion problems is the use of clamps, jigs, or fixtures to hold the work in a rigid position during welding. In this way, we balance the shrinkage forces of weld metal with sufficient counter forces to prevent distortion.
For example, when we weld these two plates, we know that when the weld metal cools, the plates will distort, like this. However, if we hold the plates perfectly rigid with clamps or jigs, the restraining forces here prevent the plates from moving. Consequently, the weld must stretch as it cools. Now, after removing the clamps, we see that almost all distortion has been eliminated. But in most cases, the plates to be welded are merely parts of a structure, and other sections will continue to hold the plates as rigid as if they were clamped permanently, thereby reducing distortion to a minimum. Here is a practical application of this principle. These heavy fixtures clamp the aircraft tubing of this fuselage so rigidly that distortion is impossible. The type of jig or fixture required will be determined, of course, by the nature of your welding job. Here's a setup where we have every possible shrinkage force balanced with other forces. The more shrink pulls, the more exhausted he becomes. Well, that'll take the starch out of him for a while. Remember that controlled shrinkage prevents distortion. So be sure to apply one or all of these 3 rules to every welding job. Reduce the effective shrinkage force. Make shrinkage work for us. Balance shrinkage forces with other forces. Arc welding is the truly modern method of fabrication. It is one of the great tools with which the leaders of modern industry today are building a new world of tomorrow.